The microphone? Yeah. I'm sorry, what was that? So in my talk today, I would like to describe for you a program that I've been involved in recent years. To try to develop a method called the density matrix renormalization group as a practical way to carry out, do effective truncations in the nuclear shell model. The work that I'm going to be describing has been carried out primarily in collaboration with Bhupender Thakur, who is now at LONI at LSU, and other participants in various aspects of this project have included Nicu Sandulescu from Bucharest and Orsay, and Jorge Dukelski from Madrid. So, a brief outline of my talk. I'd like to begin with some brief motivation, a little brief historical motivation as well. I discussed a little history of the DMRG and an overview of some of its key elements. I'm going to then describe how we apply it to the nuclear shell model. Then I'm going to describe some sample test results to try to, first of all, convince ourselves and also to convince you that it does work well as a means of providing a viable truncation strategy for large-scale shell model calculations. And then I'll turn to a little bit of future outlook. So, some very brief motivation. Much of this is already familiar to all of you. The traditional nuclear shell model, and by that I mean the shell model that we've been using for the last 50 or 60 years, in which we assume an inert core and distribute the remaining nucleons, the so-called valence nucleons, over a limited number of active shells. Now that's a dramatically less ambitious project than the so-called ab initio shell model, which Jerry would have been speaking about had he been here. But nevertheless, as I'm going to convince you in a few moments, even the traditional nuclear shell model runs into major computational limitations. In particular, let's consider a description of nuclei in the 1F2P shell, in which we assume a doubly magic inert calcium-40 core and distribute the remaining neutrons and protons over the orbits just of the next major shell, the FP shell. Now, if you, and I'm going to, for simplicity, just talk about the number of 0+ configurations. You can imagine that if you talk about the number of configurations with all possible angular momenta, it would be much, much, much larger. But consider a nucleus like titanium-44, 2 neutrons, 2 protons. The number of 0+ configurations is quite small, quite manageable, just 158 of them. By the time you reach chromium-48 with 4 neutrons and 4 protons, you already have over 40,000 0+ configurations, starting to get a little bit more difficult, but still quite straightforward. By the time you reach nickel-56 with 8 neutrons and 8 protons, just 0+ configurations, there are over 15 million of them. And if you were to go up to zinc-60 with 10 neutrons and 10 protons, there would be greater than 10 to the 10 0+ configurations. So trying to treat this without any further means of truncation becomes extremely challenging. So, what I claim is that what one needs is a reliable means of truncating the space, and ideally where one carries out this truncation dynamically, namely where you let the truncation be dictated by the interactions. And I'd like to, what I will tell you is that we have been developing for several years the density matrix renormalization group for precisely this purpose, as a dynamical means of truncating the traditional nuclear shell. Let me give you a brief historical overview of the DMRG in general. It was first introduced in the early 1990s by Stephen White as a means of treating the properties of quantum lattices. And in that regard, it was enormously successful, especially for one-dimensional lattices. The original formulation for the description of quantum lattices was based on an iterative inclusion of the real space lattice sites. As a site is added, you carry out a truncation of the number of many-body states to the same number as you had before you added that additional site. And then you go on and add the next site and go on down the line. In this process of carrying out a truncation, what you then do is to renormalize all operators that are necessary to describe the problem for use in that truncated space. And then you continue to iterate, adding all the sites, and in fact, as you'll see in a little while, you iterate back and forth until you eventually reach convergence. And indeed, the method of doing this truncation, as I'll be showing you in a little while, is based on density matrix considerations. That's the reason it's called the density matrix renormalization. This process, this method, which was originally introduced to describe quantum lattices, was subsequently reformulated so that instead of iteratively adding real lattice sites, you could iteratively add either single particle momentum or energy levels, and then go through the same process. You have a problem with a set of single particle levels, whether in momentum space or energy space, and you iteratively add them using the same general approach that I was talking about, and that I'm going to talk about a lot more as times go on. This reformulated version has proven enormously successful in a wide variety of strongly correlated many-body systems. For example, in describing problems in quantum chemistry, in describing small metallic rings, in describing two-dimensional electron systems. And these successes suggested to us its possible use in the description of another finite Fermi system, the atomic nucleus. So that's what we set out to do. So let me now tell you about the key elements of the general DMRG procedure. Then I'll talk about how we have to apply it in the nuclear context. So one begins with an introduction of sites, not real space sites as I talked about earlier, but an introduction of an ordered set of sites which in the nuclear context is going to represent single particle orbits. And for us, these single particle orbits will be spherical. Because if you introduce them as deformed single particle orbits, as you can, you have the difficulties of restoring angular momentum invariance in your system. So you have some set of single particle levels labeled, ordered. Then there's a process of what I'll call enlargement. What do I mean by enlargement? You start with a block which contains a set of sites, the first set of group of sites, which I'll refer to as B. You have a certain number of states when you've considered that set of sites B. And now what you do is you enlarge it to add, oh, that's right. I even have one in my pocket somewhere. Okay. You enlarge it to add, see how you add another site, creating an enlarged block that I call B prime. And then you also have all the rest of the sites, which we collectively refer to as the medium. It's all the rest of the sites. The next key step is